Hello everyone. Today we're going to give the final presentation on our final year design project. Our project name is Diago and our team name is bfame. Our team members are Bill Chi, Frank Liu, Armanit Garg, Michael Tsai, and Eason Zhu. Here is a brief overview of the stuff that we're going to cover today. We'll first talk about our motivation behind Diago and some requirements and specifications, and then jumps into a detailed explanation on our design decisions and Diago's internal architecture. Followed by that, we'll present you a real end-to-end live demo of using Diago for an actual load test, and then we'll discuss about some verifications and validations that we performed, which includes our user activities, and then last but not least, we'll share our reflections and learning outcomes throughout this project. The first section is requirements and specifications. As we all know that testing is an important step in building microservice-based architectures. It helps developers to determine a service bottleneck and to check whether a service can be scaled up or not. In most cases, testing requires a relatively large amount of load to be simulated, and this is hard to achieve with only a single machine due to its limited CPU and network. Thus, a distributed load testing framework solution is needed. There are some solutions currently out there in the community, such as Locust. However, after some research, we found that there are several problems with the current solution. First, the Locust deployment process is non-trivial and will add extra operational costs. Also, it doesn't have out-of-the-box support for simulating disaster scenarios. And finally, Locust was not designed to test applications on Kubernetes. And just to provide more context on Kubernetes, it is a containerized service orchestrator that aims at using cloud resources effectively. And it has multiple useful features that can support microservices on the cloud. It supports horizontal autoscaling of services. It has load balancing, disaster recovery, and it saves costs and is easy to deploy. Observing the statistical result from the community, in 2019, over 78% of the respondents said that their companies are using Kubernetes in production. And from this, we can see that Kubernetes is rising and being widely adopted in the tech community. We also noticed that the current community is actively looking for a distributed load testing framework solution for Kubernetes. Vegeta is an open source load testing tool that runs on a single machine, and as you can see that this feature request is posted in 2018, and this issue still remains open today. And with all these being said, it becomes obvious that there is an apparent need for a testing tool that is designed to run on Kubernetes. And of course, it should be easy to deploy, be scalable, and keep operation costs low. And on top of that, we have a bonus target that is to be able to simulate disaster scenarios using our tool. This initial idea came from Armanit when he was working for a startup called Simo.ai and was trying to find such a solution. So to summarize, we position our product Diago as an open source, distributed performance testing framework written in Go and designed for Kubernetes. So now let me pass on to Armanit, who will give us a detailed view of our design and architecture.
Design, implementation, and deployment. We started off by researching basic requirements for a load testing framework. We had meetings with Symbol to get a better understanding of what they were using for load testing and what their ideal system was. At the time, they were using Locust, and so we decided to figure out how we can make a better version of it to run on Kubernetes. In order to have a clearer understanding of what we were developing, we first came up with a workflow from the user's point of view. Here, the user would submit a load test to Diago. Diago would produce load for the service under test. Diago would send real-time metrics to the user's metric system, and Diago would send a final response from the load test back to the user. Since we were designing for Kubernetes, we decided to use Golang. This is because Golang is one of the most popular languages used for Kubernetes-based tools. It is also quite suitable for distributed systems with Go routines and channels at its core. To make the project more open source friendly, we scraped through multiple Golang projects like Prometheus and Jaeger tracing and came up with a structure that works best for us. We approached our design from a user's point of view. We wanted APIs to be first-class citizens for Diago. Additionally, we defined some constructs, like a test template, which defines what runs as a part of a test, and a test instance, which is a single run of a test. More on these later. We wanted users to be able to use their own monitoring systems for recording results of a load test. For this, we decided to use Prometheus's format for exporting our metrics. This is supported by various monitoring systems other than Prometheus, like Datadog and New Relic. After consulting with Professor Patrick Lamb, we came up with an approach where individual results from workers can be compiled into a single one for the user. Here, the leader still has the flexibility of aggregating results and send these back to the user and their monitoring system. Behind the scenes, we decided to opt in for a leader-worker-based architecture where the leader distributes work to the workers and the workers run the actual load test. Additionally, with the help of Kubernetes' API, we could spin up our workers dynamically. This means worker could be on a separate K8s node, which is good for managing load on the cluster. And finally, Kubernetes can also control cleanup, which means less work for Diago apart from communicating with the Kubernetes API. Consider a load test with 3,000 requests per second. The first thing we do is talk to the Kubernetes API and spin up 3 workers, each with 1,000 requests per second frequency. Kubernetes will spin up these 3 different pods, each of which will first establish a bidirectional gRPC communication back with the leader. The cluster discovery comes out of the box with Kubernetes and Diago being able to specify a worker's configurations. Once the workers are connected to the leader will send each worker its request payload and the number of requests it needs to simulate. The worker will then run the load test and simultaneously send some runtime metrics back to the leader. The leader will also compile these metrics and start reporting them to the user's monitoring system. Once the load test is complete, the workers will send a final result from them back to the leader. The leader will compile this result, send it to the monitoring system and also to the user. At this point, we decide to keep the workers around for a little bit. This is just to be able to handle any dynamically generated load tests or if the user wants to retry their previous load test. Once the workers have no more work, they can be terminated by Kubernetes or by the leader, and we can go back to the original cluster state. We wanted Diago to be extremely easy to deploy so that users can try out our software without having to do too much setup. To achieve this, we use Kustomize, which is a Kubernetes-based extension allowing us to host configurations on GitHub. This means that users can run a single command and without having to download anything, they can install Diago on their cluster. In order to support our users even further, we wrote a wiki on GitHub so that they could get all the information they need in one place. We also added go.comments, which can be accessed online. This would allow users to check out how Diago is implemented for deeper dives into the software. Going back to our original intention during the design phase, we decided to compare Diago with Locust. As you remember, Diago only requires one command to set up, whereas with Locust, a lot more manual intervention is required. Locust configurations are also not managed by the maintainers, whereas that is not the case for Diago. Here are some more differences between Diago and Locust. A major difference, however, is that Locust started out as a single node load testing software, which was eventually extended to support distributed load testing. This is not the case for Diago, which has distributed load testing as a part of its core.
We'll now perform an end-to-end load test demo using Diago. For this demo, we have Diago set up in a Kubernetes cluster running on the cloud. Diago exposes a web application that users can use to manage their tests. Let's head over there right now. On the Diago homepage, you can see that we have a navigation bar. This bar lets us navigate between the homepage and access other resources such as the GitHub repository or the Diago official wiki. On the actual content of this homepage, we have 2 tables. We have the active table, which shows all the active test instances, and we also have the finish table that shows test instances that have already finished. We also have a search bar for looking up test templates, and we have a way to create a test template. Let's create one right now. The Create Test Template page lets you create a test template, which, recall, basically defines the blueprint of a test. For this demo, we will create a unique identifier for this test template called capstone demo. A test template can have multiple jobs. Each job defines how to test a specific entity. In this case, we will be testing HTTP endpoints, and we will have a single job. Now, Diago is really flexible in that it supports the ability for engineers to create their own custom workers to perform custom testing behavior. As long as you implement a worker that implements the gRPC interface of the leader, you can write a custom worker that potentially achieves any type of behavior, such as persisting state, or even testing using a different type of protocol as opposed to HTTP. For this demo, Diago comes out of the box with a default worker for us. It's called small worker. And this worker is specifically for testing load testing HTTP endpoints. It has a capacity of 200 requests per second, and for this test template, we're going to specify to perform a test of with 900 requests per second. Therefore, we should see the Diago leader spinning up 5 small workers to support the frequency. For the duration, we will specify 5 minutes, so 300 seconds. For the HTTP method, we will specify a GET request. For the URL, we will paste this URL, which is the endpoint of a dummy service we have running inside of the same Kubernetes cluster. This dummy service, in fact, has 3 instances of it running. These instances are known as pods in terms of Kubernetes terminology, and the dummy service is configured to basically return a random dummy response, and there's custom status codes, and I believe the dummy service is configured to send failure responses about 25% of the time. And lastly, this endpoint itself is eternal to the Diago cluster. If you had a testing framework set up outside, it would not actually be able to hit this endpoint. And so that's another benefit of being able to run Diago on Kubernetes. As you can see here, we can add another job if we wanted to, but we're only going to have a single job for this test. Recall that Diago has the ability to perform chaos testing, which lets us perform disaster simulation. This is particularly useful for this case of the dummy service because it allows us to see how it handles failure and recovery under a load test. We can specify a namespace, default, and a selector, app:dummy. These 2 fields are selectors and Kubernetes concepts to help us specify the dummy service. Next, we specify a timeout, 60 seconds, meaning that 60 seconds after the start of the load test, we want Diago to perform chaos testing and cause the dummy service to fail. For count, we specify 3, meaning we want all 3 pods of the dummy service to fail. Click Submit to create the test template. Let's search for the test template we just created, Capstone Demo. We now enter the Capstone Demo's test template page. This page has some high-level information regarding this test template. At the top, we can start a test instance or we can edit this test template. Next, we have a dashboard, request rate. It's currently empty because we haven't started any test instances. We also have an executions table, which shows all of the past and recent executions of test instances. We also have a test schedules table, which shows test schedules that have been scheduled for the future. You can create one and specify a cron spec and have a test instance run periodically, which is a very useful feature. Let's start an ad hoc test instance now. After the test starts, we'll have a new row in the executions table. We can also find a row like this back at the home page. On the home page, in the active test instances table, we see a new row corresponding to the test instance we just created. The test template is Capstone Demo, and there's a unique identifier for the test instance ID. The type is ad hoc because we created this on the fly, not through a schedule, and the status is processing. It also shows the time that we created this test instance. If we click on the test instance ID, this takes us to the test instance details page, where we can see some high-level information regarding this particular execution of a test template. Right now, the table is mostly empty, but we can already see some data coming in real time. We will now wait until this test instance is done processing. Okay, so roughly 5 minutes have passed, so this test should be done running now. There's also a button up here called Stop Test Instance, where you can click this and forcefully stop the test anytime you want. So let's just quickly refresh the page here. We can see that the status of the test instance is a success, which is good, and we can now evaluate the time series data. So for request rate, we can see that the duration is roughly 10 minutes, which is consistent with the parameters of our test template. And interestingly, if we look at the 1 minute mark, we see a slight dip in the request rate and the success rate. And this is also consistent with our chaos testing configs, because we mentioned that at the 1 minute mark, the chaos tester would basically kill the 3 dummy service pods. And for latency as well, this is consistent because around the 1 minute mark, we see a slight rise in the latency. And for bytes rate, we see a slight dip in the number of bytes received. And that's precisely because during that period of time, the pods were down. And so the requests we were sending, we were not getting responses back for them. We also have a whole section here regarding aggregated metrics for this job. We have a whole bunch of metrics related to the duration, time range, throughput, all the different percentiles for latency, the different status codes. And of course, beside each of these metrics, we have help text that kind of guides you and explains what each of these metrics mean. And lastly, we have another box here that talks about the metrics regarding the chaos testing results. So clearly we see here that 3 of the pods for the dummy service were essentially destroyed. And as well, one thing to note is that Grafana is a very popular metrics tool, and we do offer integration with Grafana. And so there's a link here, and if we click on this link, this takes you to the Grafana dashboard for Diago. We have some basic graphs here that we've already seen, but there's another dashboard as well that you can go to. So this dashboard is a great debugging tool for engineers because it shows you kind of the internals. It shows you the Diago worker capacity and available versus total capacity. It's also very interesting and useful because it really shows you the power of Diago running on Kubernetes and how it can use Kubernetes to dynamically scale workers up and down. So if we zoom in here on this section, which corresponds to the load test we just performed. Right, so if we focus on the first graph here, the Diago worker capacity. So before we started the load test, we had 0 workers because we have not written any tests yet. And when we actually initiate the load test, if you recall, the frequency we specified is 900 requests per second. And since each worker, the small worker provided, has a capacity of 200 requests per second, we need to spin up 5 workers. And so if you click here, for the duration of 10 minutes, we have exactly 5 workers. Next, if we look at the Diago available versus total capacity, again, before the load test, we have 0 capacity because we haven't started any tests. Once the test starts, at the very beginning, the yellow line is the total capacity in the cluster. It's 1,000 because we have 5 workers. Each one specifies a capacity of 200. But the available capacity at the beginning is 100. Why? It's because our load test requires 900 requests per second, so it's using up 900 out of the total 1,000 capacity, which is why we're only left with 100 capacity available. However, after the test finishes around this mark, we get the capacity back. So the available capacity becomes 1,000 again because the load test is over and the workers are now free. And during this last duration of time, what's basically happened is the workers are still up and running because there's a chance that the user might initiate another load test. But after the specified interval here, Diago is smart enough to realize that, okay, the workers are not being used, and so it's not useful to have them up running and using costs, and so it basically dynamically scales the workers down back to 0.
To reach the current state of our product, we have done several cycles of different verification and validation. For the code, we use automated unit tests to maintain code health and stability throughout the development cycle. Each merge request requires these tests to pass before approved to be merged into our stable branch. Currently, we have 88% test coverage measured by CodeCov. This, along with code health, is displayed on our main GitHub repo page. We also have automated integration tests to ensure that all 14 of our public-facing APIs each achieves the task it is designed for. For our user interface, we do internal demos and exploratory testing on a bi-weekly basis to ensure the UI experience matches our design. The process is similar to what we did in the demo video, clicking around, making and running load tests. Externally, we ask another team, the tutor team, to test our UI. Here are some feedback highlights from them. Overall, they think the UI is smooth and has some nice design choices. They also provided some valuable criticisms. For example, they suggested adding units for graphs in load testing results page, as well as improving visual distinction between failed and done status. Here's a look of our old UI design. And as you can see, in the new design, we have better color contrast between different status codes. We added units for all measurements. We also added help text, which is the small question mark, beside each terminology to explain what it means. We then increased the overall area used to display the results by shrinking the area used to display the less important information, such as instance ID and test ID. Another testing we did is on overall software usability. We used one of our user activities to conduct this test with 3 external users who all have background in Kubernetes. The goal is to simulate what our potential users would experience from installing the software to conducting load tests. We provided our testers with an already configured Kubernetes cluster, as well as the Diago's installation and user guide provided on the GitHub repo. We then asked the testers to follow the guide and experience the software, then report on the simplicity of the installation process, the user experience of the web page, as well as how likely they will use Diago. All three of our testers liked the one command setup for its ease of deployment. They also like how easy it is to scale with no manual interventions required. Two of our testers mentioned that the UI integration with monitoring system is very convenient. Some criticisms we received include the lack of controllability over the load tests. We addressed this by including it as a future feature in the roadmap. Another feedback we got from one of our testers is that the terminology of test template and test instance is quite confusing sometimes. We have since added a clarification on these terminologies on the Diago wiki page. Finally, we found two of our testers both requesting for the ability to run a bash script as a job. They wish to conduct more complex sequential workflows, such as logging into a page and then perform function XYZ. Overall, we received pretty positive feedback from our testers. Here are the numeric grading they provided us on how likely they will use Diago, as well as how easy they think the setup process is.
We also tested Diago on real-world services, the first of which is Tutoru.tv. We approached Philip to test some of their endpoints and staging. Their services are not hosted on Kubernetes clusters, but we thought it would be a good application of Diago, since the product is rapidly growing, and their APIs need to be able to keep up with this growing demand. To do this, we set up a series of load tests, each ramping up the volume of requests, maxing out at 2,000 requests per second. Here is a screenshot of the load testing result from one of the endpoints. As you can see, the request rate remained at a steady 2,000 during the 10 minutes of load testing. The service was able to keep up with this rate, since the latency remained consistently low. Another service that we tested is MoonPod, an app that currently has 10,000 average visits per month. We use the same methodology as we did for Tutoru. However, during the process of ramping up, we crashed the app using a load of 1,000 requests per second. From this, we were able to conclude that the services need autoscaling in order to handle more traffic. Here are some screenshots of the Heroku dashboard for the application. During the load test, the response time shot up rapidly, and the app crashed soon thereafter. Next, I'll present a summary of the various aspects of reflection regarding our project as well as the process we took to build it. We determined that Diago has limited negative impact on society. Even in the wrong hands, the tool wouldn't be very practical for DDoS or brute force attacks. The cluster's egress IP is fixed and easily rate limited. As a feature, rate limiting is offered directly by cloud service providers such as Azure and AWS, and is a given on modern-day production services. The functionality of Diago will not displace current employees. Typically, manual orchestration of tests is done by QA or software engineers whose jobs involve many other tasks. Diago doesn't collect any personal or third-party data, which means that the privacy of its users is protected. We licensed Diago under Apache License 2.0 for a variety of reasons. The first is that its dependencies limit us to the GNU General Public licenses. However, this is not a downside since these licenses offer permissions that make Diago suitable for many different purposes, which makes it highly adoptable. The license also limits the liability of contributors towards the exercisers of the license, which encourages more developers to join in contributing. The copyright of Diago will be jointly owned by all of its contributors. We reflected upon and took action according to the feedback given during our peer activities. In an architecture review of our system, Team's executives found our diagram unintuitive. They were also unable to understand the purpose of the chaos simulator. We addressed these concerns by clearly labeling each component and elaborating on the chaos simulation during our demo. The team also commented on the large amount of traffic between the leader and the workers, which we took note of and listed as a priority to address in our roadmap. In a presentation review, Team Oasis noticed how we neglected to mention our testing strategy. We addressed this by expanding on our unit testing and integration testing. They also recommended that we should more clearly explain the advantages of Diago over other load testing options, which we did by conducting several user activities focused on usability. Listed here are some of our learning outcomes, among many others. With hands-on experience, we learned to design distributed systems and work with Kubernetes. We learned about the best practices for managing open source projects as well as Go projects. We learned about how to license our project and what permissions our license offer to the exerciser. We learned about managing deadlines for our project and organizing tasks that need to be done. Finally, we learned about setting up intuitive documentation as well as how to cater to first-time users of our product. That's the end of our presentation. Thank you for listening.